Welcome to the deep dive. Today's date is June 16th, 2026, and we are looking at a really critical moment in the physical evolution of artificial intelligence.
Yeah, it's definitely a turning point. We're at this stage where things have to change.
Exactly. And our mission for you today is to understand these invisible physical walls that are just, well, suffocating AI data centers right now. We're
Yeah.
talking about massive power limits and these huge bandwidth bottlenecks.
Right, because the hardware is basically hitting a wall.
Yeah, and we want to decode the radical, really microscopic hardware overhauls that engineers are deploying to smash right through those walls. So to do this, we have a massive stack of sources in front of us today.
We really do. It's a lot of ground to cover.
It is. We're pulling from technical engineering papers on silicon oxynitride interposers, research from EPCO on gallium nitride power converters, and we've also got some really fierce market debate reports from Counterpoint Research, Mizuho, WCCF Tech, and KuCoin.
The good mix of the deep physics and the actual market reality, which I love.
Okay, let's unpack this because, we talk about the cloud like it's this weightless, invisible thing. You type a prompt, an image appears on your screen, and it feels like, I don't know, magic happening in the ether.
Yeah, the cloud metaphor does a phenomenal job of hiding the physical reality from the user.
Yeah.
I mean, we like to imagine our data just floating gracefully in the sky, completely detached from earthly constraints.
But the reality isn't the cloud at all, right? It is incredibly heavy, it is blisteringly hot, and it's tethered by like millions of miles of thick copper cables.
Oh, absolutely. The physical infrastructure of the internet is practically buckling under the weight of artificial intelligence right now.
Right. We hear about massive new AI models launching every single day, but we rarely think about the physical cords, the power cables, and, well, the cooling systems running them.
People just don't see that part of it, but it's the foundation of everything.
So to understand why data centers are fundamentally redesigning how they route data, we first have to understand how they are keeping the lights on, because power dictates absolutely everything else.
It really does. I mean, if you cannot reliably deliver power to a chip, that chip does not calculate, period.
Right.
And as these AI workloads scale up, they are literally outstripping the power grid's capacity. They're hitting the absolute physical limits of what our legacy systems can actually handle.
And we saw this in the WCF Tech report. Right?
Yeah, the numbers detailed in that report highlight a mandatory radical overhaul of power infrastructure by companies like NVDA and Google. They are shifting to a radical 800-volt direct current, or HVDC system.
Which sounds like a huge jump.
It is, but the necessity becomes clear when you look at the raw wattage. Like NVIDIA's upcoming Rubin Ultra platform, that's going to hit 450 kilowatts per rack.
Wow, okay.
And it gets wilder. The generation immediately following that, the Feynman platform, that one is projected to require between 600 kilowatts and a staggering 1 megawatt per single rack.
Okay, let's just contextualize a 1 megawatt rack for a moment for you listening, because that is roughly the electrical draw required to run like 1,000 average residential homes.
Yeah, a whole neighborhood.
A whole neighborhood? All condensed into a metal cabinet the size of a large kitchen refrigerator. That's insane.
It really is harder to wrap your head around.
So if we think of electricity as water, legacy 48-volt or 54-volt systems in older data centers that just can't push enough volume, I imagine it's like trying to put out a forest fire with a standard garden hose.
That's a perfect way to look at it. Let's actually take that water analogy one step further, because the distinction between voltage and current is the entire reason for this 800-volt shift.
Okay, break that down for us.
So voltage is essentially the water pressure, while current is the actual volume of water flowing through the pipe.
Got it.
To deliver 1 megawatt of power using an old 48-volt system, you have to push a massive amount of current. And high current encounters a lot of resistance in those copper wires.
Which creates friction.
Exactly. And that electrical friction generates catastrophic amounts of heat. But by bumping the pressure up to 800 volts, you can deliver that exact same 1 megawatt power using significantly less current.
Oh, I see. So less current means less friction, thinner cables, and obviously way less wasted heat.
Precisely. It solves a massive thermal problem.
Which sounds great on paper, but I have a major safety and engineering question here.
Sure. What is it?
Piping 800 volts of direct current straight into a rack of highly sensitive, multi-million-dollar computing hardware. That sounds like a massive hazard.
Oh, it absolutely would be.
Right. Like, if a single thing arcs or goes wrong, doesn't that just fry a cluster of irreplaceable GPUs instantly?
It would, yeah. But the engineering research from EPCO addresses this exact vulnerability through what they call ISOP converters.
ISOP, what does that stand for?
It stands for Input Series Output Parallel. The key thing here is you never dump 800 volts directly onto a delicate processor. The architecture totally isolates the high voltage danger.
Okay, how do they do that physically?
They are removing the bulky power supply units out of the IT compute racks entirely. Those power units are moving into dedicated, separate power racks.
Oh, wow. So you separate the power plant from the actual computer room?
Exactly.
You bring the high voltage into one secure location, step it down safely, and then pipe the manageable power over to the chips, which I guess also frees up all that physical space in the compute rack for more processors.
Yeah, it's a huge win-win for space and safety. And the technology enabling that crucial step-down phase is the gallium nitride, or GaN converter.
GaN. We've been hearing a lot about that lately.
Yeah, EPC's paper details how engineers use these 150-volt rated GaN transistors to take that 800-volt main line and step it all the way down to a highly regulated 12.5 volts for the chips.
That is a massive step down.
It is. They basically chain 8 identical modules together to distribute the load evenly. And GaN is a massive leap over legacy silicon components for this.
Why is that? What makes it better than silicon?
Well, standard silicon maxes out at a certain switching speed before it starts losing massive amounts of energy as heat. But gallium nitride has a much higher critical electric field.
Okay, meaning what, practically?
Meaning it can switch states incredibly fast while barely losing any energy at all.
And efficiency is the holy grail here.
Right.
Because any electricity that doesn't become computational math becomes waste heat.
Right.
And then, you have to spend even more electricity powering the liquid cooling pumps just to get rid of that heat. It's this vicious cycle.
Exactly. But these GaN converters, they achieve over 98% peak efficiency.
98%, that's almost perfect.
Yeah, and even under a punishing full load of 6 kilowatts, they still maintain 96.4% efficiency. Because they don't generate much heat. They don't need these massive, bulky heat sinks anymore.
Which saves even more space.
Right. The entire converter board fits into a form factor just 8 millimeters thick. So, if we connect this to the bigger picture, this specific microscopic leap in power density is the actual mechanism enabling the massive gigawatt-scale AI factories being constructed today.
That's incredible. Okay, so let's assume we've solved the power delivery problem. We can successfully feed a 1 megawatt rack without blowing the whole building up.
Right, milestone 1 achieved.
But the second you achieve that, you smash headfirst into a second physical wall, which is the data bottleneck.
Oh yeah, the data wall is brutal.
Because the GPUs are consuming all this power, doing billions of calculations a second, but they have to talk to each other to actually train these massive AI models.
Right, they don't work in isolation.
And traditional copper wires physically cannot carry the data fast enough, can they?
No, they really can't. Copper has fundamental physical limitations. When you push high-frequency data signals through a copper wire, you encounter something called the skin effect.
The skin effect.
Yeah. Basically, the data signal gets forced to the very outer edge of the wire. This increases resistance, it degrades the signal, and again, it generates heat.
So copper just sort of chokes on the data at these speeds.
Exactly. And the counterpoint research analysis on NVIDIA's optical roadmap illustrates this super rapid transition away from copper to solve this exact problem.
Right, we're seeing this massive shift to optical tech.
Yeah, look at the Blackwell platform. It utilized traditional pluggable optics alongside some early co-packaged optics, or CPO. But the subsequent Vera Rubin platform, that introduces linear pluggable optics and CPO-based NVLink switches that are specifically designed to connect 8 rack pods without that signal degradation.
And then we hit the Feynman platform in 2028. Counterpoint literally calls Feynman a gigawatt-scale design.
Which is just a terrifying amount of power.
Totally. And with Feynman, copper backplanes are entirely eliminated, like gone. It is native CPO directly on the GPU package.
Yep, native CPO is the big paradigm shift.
They are deploying OSFP XD connectors, which stands for extra density, and these literally double the electrical lanes in a single physical port. We are talking about pushing up to 3.2 terabits per second out of a single connection.
It's just mind-boggling bandwidth.
But I want to linger on this shift to optics, specifically how traditional pluggable optics work versus this new native CPO approach, because it's not just swapping a cable, right?
No, it's a completely different architecture. Traditional pluggable transceivers contain digital signal processors, or DSPs.
Okay, what do those do?
When a chip sends an electrical signal, the DSP has to process and clean up that signal before it can actually be converted into light and sent down the fiber optic cable. And those DSPs demand a massive amount of power to perform that cleanup.
I picture it like trying to have a rapid-fire, really intense conversation, but you're forced to hire a translator.
That's a great analogy.
Right. The translator has to painstakingly listen to you, decode every single sentence, and then repeat it to the other person. That translator is the DSP chip. It takes time, it consumes energy, and it bottlenecks the entire conversation.
Exactly. And the new linear pluggable optics, and especially native co-packaged optics, they remove that translator entirely.
So it's just direct communication.
Yeah, it's like achieving telepathic communication between the chips. Bypassing that middleman slashes the latency and dramatically cuts down the heat.
So where exactly does the laser go in native CPO?
Native CPO places the optical engine, the actual laser that's converting the data into light, as physically close to the switching chip as possible. In a lot of designs, it sits on the exact same pigeon silicon as the processor itself.
Here's where it gets really interesting because, writing native CPO on a sleek investor roadmap is easy.
Oh yeah, drawing it on a slide is easy.
But the actual microscopic physics of integrating lasers onto silicon chips, that is a monumental engineering hurdle. You can't just tape a laser pointer to an AI chip.
No, you definitely cannot. It requires fundamental breakthroughs in material science.
Which brings us to that Archive paper from the researchers at Zhejiang University and the Chinese Academy of Sciences.
Right. That paper addresses exactly why integrating lasers on standard silicon is so incredibly difficult. It comes down to something physicists call an indirect band gap.
An indirect band gap. Okay, in practical terms, what does that mean for you and me?
In practical terms, standard silicon is fantastic at conducting electricity, right? We've used it for decades. But it is fundamentally terrible at generating light.
Because of the way the electrons behave.
Exactly. When you pump electricity into an indirect band gap material like silicon, the electrons lose their energy by creating phonons, which is really just a fancy scientific word for vibrations or heat. They don't release their energy as photons, which is light. So you have this chip material that gets extremely hot, but flat out refuses to glow.
So it's literally the worst material to use if you want to make a laser.
Basically, yeah.
So how do they fix it?
The researchers propose a solution through what they call hybrid integration. They bring in a completely different material that can generate light, and they physically attach it to the silicon.
Okay, so a Frankenstein kind of situation?
Sort of. They use a technique called flip chip bonding to attach indium phosphide lasers. Indium phosphide actually has a direct band gap, so it generates light beautifully.
Okay, so the indium phosphide is the light bulb.
Right. And the specific lasers they bond are electroabsorption modulated lasers, or EMLs. They bond these onto a specialized interposer. This whole setup allows them to transmit 4 channels of 100 gigabit PM4 data.
Which totals 400 gigabits per second.
Exactly. Over 2 kilometers of single-mode fiber with incredibly clear eye diagrams.
Okay, let's definitely translate some of that terminology for anyone not actively building lasers in their garage right now.
Good idea.
You mentioned PM4 data and eye diagrams. I'm assuming an eye diagram isn't a biological term, but rather some way to visualize if the data signal is actually surviving the journey.
That is a perfect intuition. If you hook an optical signal up to an oscilloscope to measure its quality, the overlapping data waves form a shape on the screen that looks exactly like a human eye.
Literally an eye shape.
Yeah. And if the eye is wide open on the screen, it means the distinction between the ones and zeros is perfectly clear. The data is pristine.
And if it's struggling?
If the signal is degraded, messy, or just filled with noise, the eye on the screen looks closed or really blurry.
Got it. And what about PM4?
So older systems use simple binary, just on or off, 1 or 0.
Yeah.
PM4 uses 4 different levels of signal amplitude.
Oh, so it's doing twice the work.
Exactly. It crams twice as much data into the exact same signal without having to increase the speed of the laser itself.
So they are packing way denser data into the light, and this open eye diagram proves it arrives perfectly intact.
Yep. It's brilliant engineering.
But, the absolute key to this SIVE paper isn't just the laser itself. It's the interposer material they bonded the laser to.
Yes. The silicon oxynitride.
Right. It's not standard silicon. It is silicon oxynitride, or SiON. Why introduce a whole new material here? Why not just use standard silicon, which the global semiconductor industry already knows how to manufacture by the billions?
It really comes down to the physics of light propagation. Standard silicon has a very high refractive index contrast.
Okay.
When light travels through a standard silicon waveguide, that high contrast means the light is tightly confined within the channel. And because it's so tightly confined, Any microscopic manufacturing error, even like a stray cluster of atoms causing roughness on the wall of that microscopic tunnel, it causes massive scattering losses.
So the light just bounces around and gets lost.
Yeah, exactly. The light hits the bump, bounces off unpredictably, and just leaks right out of the channel. But Scion has a lower refractive index contrast.
Meaning what for the light?
The optical modes, which is the actual physical size of the light beam traveling through the material, are larger.
I think of it like the difference between driving a bobsled down a narrow, winding ice chute versus driving a truck down a massive, multi-lane highway.
Okay, I like that.
If you scrape the wall in the narrow bobsled track, you crash immediately. But if there's a small bump on the edge of the wide highway, you barely notice it. Scion is a wide highway. It is far more forgiving to manufacturing imperfections.
What's fascinating here is that it has a significantly higher fabrication tolerance. You just do not need absolutely flawless sub-nanometer perfection to keep the light safely contained within the waveguide.
Which makes manufacturing it at scale actually possible.
Exactly. And furthermore, Scion is remarkably less sensitive to temperature changes. It has a very low thermal optic coefficient.
Why is that important?
Well, consider the environment. These lasers are sitting fractions of a millimeter away from a GPU that's running at hundreds of watts. The thermal environment inside an AI server is completely brutal.
Right, we talked about that waste heat earlier.
Yeah, and standard silicon's optical properties shift and warp wildly when it gets hot, which throws the data signal completely out of alignment. But Anside remains optically stable under extreme heat.
So it solves one of the most critical thermal constraints of that 1 megawatt AI rack.
Precisely.
They literally changed the playing field by altering the composition of the glass guiding the light.
It's amazing stuff.
It is. The engineering is flawless in the laboratory setting, but taking this technology to global mass production, well, that has triggered a massive rift in the financial markets this exact week.
Yeah, the markets are having a field day with this.
It is the classic difference between building one perfect handcrafted concept car for an auto show and manufacturing a fleet of 10,000 reliable minivans that won't break down on the highway.
That's the reality of scaling hardware. We are watching a fierce debate play out in real time, which is summarized comprehensively in the KuCoin article.
Right, outlining the clash between a semi-analysis report and the prominent analyst known as Serenity.
Exactly. Billions of dollars in market capital are basically riding on who accurately predicts this timeline.
So let's impartially examine the semi-analysis perspective first. They present a deeply conservative systems engineering argument that's based on repairability.
Yeah, repairability is a huge sticking point.
Because co-packaged optics fundamentally permanently integrate the laser and the switching chip, right?
Yes, they are fused together.
In today's data centers, if a pluggable optical cable fails, a technician just walks down the aisle, unplugs the dead cable, throws it in the trash, and plugs in a new $50 replacement. It takes 30 seconds.
Super easy.
But with CPO, if one microscopic laser fails, you cannot just swap the cable. You might have to scrap the entire highly expensive, deeply integrated switching chip.
And it represents a massive yield and repairability risk. I mean, when you integrate dozens of components, the total system yield drops exponentially if even one part has a minor failure rate.
So it's incredibly risky for data centers.
Very. Because of this risk, semi-analysis argues that the timeline for large-scale CPO adoption is being pushed back to 2028 or maybe even 2029.
So what do they think happens in the meantime?
They suggest the industry will heavily rely on an intermediate architecture called near-packaged optics, or NPO, to bridge the gap.
NPO, how is that different?
NPO moves the optics very close to the chip to gain that speed, but it keeps them on a pluggable baseboard to retain that vital replaceability.
A compromise.
Yeah. And the market reacted violently to this report, triggering a sharp sell-off in optical networking stocks like Coherent and Lumentum.
But wait, didn't NVIDIA just announce they are already shipping their Spectrum-X CPO switches?
They did.
So if the hardware is literally leaving the loading dock right now, how can a report claim the timeline is pushed back to 2029?
Well, this brings us to the bullish counter-argument presented by Serenity, which is also supported by a Mizuho Research note. And that Mizuho note bluntly called the optical stock sell-off stupid.
Stupid. That's a strong word for a financial report.
It is. Serenity's core argument is that semi-analysis is analyzing NVIDIA as if they were a standard captive customer in a normal supply chain. But NVIDIA isn't normal. They are the architect of the entire AI ecosystem. They write the rules.
Right. They possess immense financial incentive to force the supply chain to compress the hardware cycle.
Exactly.
If copper wires and traditional pluggable optics are the primary bottleneck preventing NVIDIA from selling more multi-million-dollar GPU clusters, they will move mountains and deploy limitless capital to just brute force a solution.
This raises an important question, though, which the Mizuho report validates by pointing out that Lumentum already has hundreds of millions of dollars in CPO orders locked into their books for 2027.
Wow. Real money, not just projections.
Right, the orders are not theoretical. They are contracted. So are investors currently trading on the end game of the technology, meaning everyone acknowledges CPO is the final inevitable destination, rather than accurately pricing in the realistic, messy slope of adoption?
Right. Semi-analysis maintains the physical engineering will simply take time to perfect no matter how much money you throw at it.
Well, Serenity argues NVIDIA has the market power to literally bend time.
The reality is likely somewhere in the middle, right? A heterogeneous environment where NPO, pluggable optics, and CPO coexist for years, just deployed based on the specific thermal and speed constraints of individual data centers.
That's the most realistic outcome.
So what does this all mean for you navigating this landscape? Why should you care about the refractive index of silicon oxynitride or the voltage step-down of a gallium nitride converter?
It's a fair question to ask.
Because every single time you utilize a new AI tool, every time you prompt an image generator or query a large language model to analyze a document, you are writing directly on top of this exact physical infrastructure.
You really are. The velocity of AI's evolution is no longer strictly bound by software engineers writing smarter algorithms in a vacuum.
Not at all.
The frontier of artificial intelligence is now a brutal, physical war against heat dissipation, the hard limitations of global power grids, and the literal speed of light traveling through glass.
The tech industry is being forced to execute a top-to-bottom overhaul of its power delivery, moving to that 800-volt direct current managed by GaN isolation.
And a total overhaul of its data delivery, shifting to co-packaged optics mounted on those Scion interposers.
They are reinventing the hardware architecture entirely just to ensure that artificial intelligence doesn't suffocate on its own physical limitations.
All of this groundbreaking material science and power engineering is happening right now, completely out of sight, locked inside massive windowless buildings all over the globe.
Which leaves you with a final thought to mull over as you watch these models get smarter every single week. Well, if human engineers are currently required to completely reinvent global power distribution, engineer microscopic light-bending silicon, and push the very laws of physics to their breaking point just to feed the AI models that exist today, what kind of impossible, world-altering physical infrastructure will be required when these AI systems become smart enough to start designing their own successors?
The messy, unyielding constraints of the physical realm might be the only thing holding them back.
We'll leave you to think on that. Until next time.